Hello viewers, in today's class we are going to discuss one important problem from integrals using the concept of beta and gamma functions, right? So here we are once again going to solve another problem from the concept of beta and gamma functions. So here we'll solve this integral which is 0 to infinity, and we have dx over x square plus 1 raised to 4, right? So we'll see how using the properties of beta and gamma functions we can solve this integral easily, right? So let us call this integral as I, right? Now see here we'll use the method of substitution, and we'll take this term, that is x square equal to t, right? So x square is equal to t, so x can be written as square root of t. Now let us differentiate x with respect to t. So we have dx over dt, and the derivative of square root of t is 1 over 2 times square root of t. So we can now write dx is equal to dt over 2 times square root of t. Now see here the limits of integration vary from 0 to infinity. So when x is equal to 0, then the value of t is also equal to 0. And when x is tending to infinity, then t also tends to infinity. So now we can rewrite this integral in terms of this new variable. So we can now write 0 to infinity. For dx we can write dt over 2 times square root of t, and here we have x square is equal to t, so we can now write t plus 1 raised to the power 4. So now let us rewrite this integral by taking 1 over 2 outside the integral. So we have 0 to infinity, and we have here dt over square root of t, and here we have t plus 1 raised to the power 4. Now we can write I as half, and then we have 0 to infinity. Now see here we have square root of t. So we can write square root of t as t raised to half. So taking t raised to half to the numerator, we have t raised to minus half, and in the denominator we can now write t plus 1 raised to 4, right? So now we have this integral, right? Now here we'll make use of the concept of beta function. Now see, the beta function is defined as beta m comma n is equal to the integral 0 to infinity x raised to m minus 1 divided by here we can write x plus 1 raised to m plus n, right? So the beta function is defined by this integral. So our next aim is to compare, or to compare this integral with this one by finding out the values of m and n. So now see, here we have 0 to infinity. Here we have t raised to minus 1 over 2, t plus 1 raised to 4. Now this integral is similar to this one, except the variable, because the variable may be treated as a dummy variable. So this is not going to make any difference. So this integral is similar to this one. And if we compare the powers here we have t raised to minus half, here we have x raised to m minus 1. So we can take m minus 1 is equal to minus half, and here we have 4. So m plus n can be taken as 4, right? Now here m minus 1 is equal to minus half, so from here m is minus half plus 1, that is simply half, right? Now taking m in this equation, we can find out the value of n. So n is 4 minus m, so that is 4 minus half, that is 8 minus 1 over 2, that is 7 over 2, right? So now this integral I can be written like this, that is half, we have 0 to infinity, and t raised to minus half, right? Now see, t raised to minus half is m minus 1 and m is half. So we can now write it like this, half minus 1. And here we have t plus 1, t plus 1 raised to 4, and 4 is equal to m plus n. M is half and n is equal to 7 over 2, right? And we can easily verify that half minus 1 is minus half, and half plus 7 over 2 is equal to 4, right? So here we have dt. So now this integral is equal to the beta function, that is beta of m comma n. M is half and n is 7 over 2, right? So now we have to find the value of beta half comma 7 over 2. So now we can express the beta function in terms of gamma function by utilizing this result, that is beta m comma n is gamma of m gamma of n divided by gamma of m plus n, right? So we can now write half. Here we have gamma of half, then we can write gamma of 7 over 2, and then we have gamma of half plus 7 over 2, right? Now see, we know that gamma of half is equal to square root of pi. So this is a standard result. Gamma half is equal to square root of pi. Now we have this term, that is gamma of 7 over 2, right? So gamma of 7 over 2 can be expressed like this, that is 5 by 2 times 3 by 2 times half times gamma of half, right? So to express gamma of 7 by 2 like this, we have used an important relation, that is gamma of n plus 1 is equal to n gamma of n, right? So now if we take n is equal to 5 by 2, then we have 5 by 2 plus 1, which is equal to gamma of 7 over 2, right? So gamma of 5 by 2 plus 1 is equal to 5 by 2, 5 by 2, then gamma of 5 by 2, right? So successive application of this result can give us this result, right? Then we can write 5 by 2 as 3 by 2 plus 1, and again applying this result to this expression, we have 5 by 2 times 3 by 2 gamma of 3 by 2, and then gamma of 3 by 2 can be written as half plus 1, which is half times gamma of half, right? So this is 5 3s are 15, and this is 2 2s are 4 2s are 8, and gamma of half is square root of pi, right? So now in the denominator we have gamma of half plus 7 by 2, which is equal to 4. 7 plus 1 8, 8 over 2 is 5, 4, and gamma 4 is equal to 3 factorial, right? So here we have used the result, that is gamma of n plus 1 is equal to n factorial. So 3 factorial is equal to 6. So now this integral it takes the form half, this is half, and gamma of half is square root of pi, and gamma of 7 over 2 is 15 over 8 times square root of pi, and gamma of 4 is equal to 6, right? So square root of pi times square root of pi is pi, and here we have 15, and in the denominator we have 2 8s are 16 times 6. So this is 3 2s are 6, 3 5s are 15. So this is 5 pi over 16 2s are 32, right? So the value of this integral I is equal to 5 pi divided by 32. So viewers, this is how by the simple application of beta function and gamma function, we can easily find out the values of these type of complex integrals.